Sai Natarajan sir.
Yes.
Good morning, welcome.
Good morning.
We'll start within a minute. Sir.
Okay, ma'am.
Good morning, all. Able to hear me? Good morning, everyone.
Good morning.
Successfully, we have completed 3 days. This is the 4th day of the FDP. Today, we got an excellent person. Sir, good morning, sir. Sai
Good morning.
Natarajan, sir.
Good morning.
Good morning, sir. So, good morning, everyone. We will start the session. Before starting the session, I request Mr. Karthik from Assistant Professor from Department of Information Technology to introduce the chief guest.
A very good morning to everyone. So it's my pleasure to welcome all the participants for the day 4 session of the Faculty Development Program on Artificial Intelligence and Cloud Services. I take immense pleasure in welcoming the resource person for today's session, Mr. Sai Natarajan, President, Duratech Solutions, Coimbatore. So on behalf of the Department of Information Technology and Computer Science, Sri Ramakrishna College of Arts and Science, I welcome you, sir. So Mr. Sai Natarajan has more than 13 years of experience in IT sector He has worked with TCS from the year 2010 to 2012 and Bosch India from 2012 to 2013. His expertise areas include big data, data analytics, data science, cloud computing, DevOps. He's also an expert in application monitoring stacks like Splunk, Prometheus, and many others. He's an expert in Spring microservices development using Spring Cloud Framework. And he has also offered training in big data, machine learning, R, Python, and cloud computing for both freshers as well as laterals from leading MNCs in India and also to international candidates. He has more than 8 years of experience in training. So with this few words of introduction, I once again welcome you, sir. So now I request Mr. Sai Nadarajan to take over the session.
Thank you, sir. Okay. I have shared my screen. Can you please confirm if my screen is visible?
Yes, sir, it is visible.
Okay. So I was planning for an agenda which will generally discuss about the machine learning, and then we will get into specific details related to reinforcement learning. But before I proceed, my main topic I have planned to cover today is reinforcement learning. So I would like to know if any specific details have been covered related to machine learning and related concepts earlier. If you can let me know, that will be helpful, so that I can plan exactly what will be the content which will be most effective for this training. So should I start with the basics of machine learning, or is it already covered that people are already fully aware, and in that case I can directly get into reinforcement learning?
Sir, machine learning basic in the sense just gives a slight introduction where the reinforcement is coming like that, sir.
Okay, madam. Fine.
Hope everyone know what is machine learning.
Okay.
Because all are faculty members, so definitely they should know what is machine learning. But
Okay.
it's still reinforcement is a little bit new. So how it's connected like that? In that way, you just give the introduction to machine learning, sir.
Okay, fine, madam. I'll just give a very fast introduction to machine learning, and then we
Yes.
will get into the
Yes, sir.
concept related to reinforcement learning straight away. Fine. So let me introduce myself. I think sir has already given an introduction about myself for a long introduction. So I mainly specialize in couple of things. One is the machine learning, deep learning, and artificial intelligence from the data science perspective. And I also work on DevOps most recently. So last 2-3 years, majorly my work had been on cloud and DevOps, where I mostly work on Docker and Kubernetes, containerizing applications, microservices development. That had been the major part of my work. So I do develop a lot of projects for clients in India as well as globally. So I mostly work with tier 2 or tier 3 vendors in Coimbatore and Chennai. So from the machine learning perspective, I've been working on Python and R since 2014. And we have done a lot of research work on text processing, computer vision, which is nothing but image processing. And to some extent, we have also worked on commercial projects on chatbots and computer vision related projects. So that had been our work majorly from the machine learning perspective. So we have done predictions for our projects using the normal tabular kind of data, using the data that can fit on pandas. So as well as data on video, images, audio recognition, image recognition, etc. So we have also done generative models in one of our projects as well. Even we have worked on 3D video generation or 3D structural generation in one of our previous projects around 4 years back, 3 to 4 years back. Fine. So coming back to the main agenda for today, which is reinforcement learning. So I want everyone to be given a clear differentiation between what is the machine learning and what is the reinforcement learning, and what is the difference between the two. Okay, so when we start with machine learning, I think, as you said, most of you might already be aware of. So, what is the prerequisite to start an ML project? So, what do we need as a prerequisite to work with an ML project? Because the algorithms are there, they are standard algorithms. So we have classification, regression, and so on. So, what is the prerequisite for a machine learning project to start? I'll try to keep this session interactive because I feel there can be more learning done in this at a smallest amount of time possible by keeping the session interactive and asking questions and then clarifying the questions with the answers. And maximum, when you start thinking, you get much more deeper learning than me just continuously talking. So that's the reason I'll try to keep asking a few questions, and you can try to answer and you can try to think about the answer, and then we can conclude and then we can keep learning further and further new things. So that would be my approach. So based on that approach, I would like to ask the first question, which is what is machine learning, or what is the prerequisite to start a machine learning project? So for example, we have a bunch of algorithms and you have to do a classification. So that is the requirement. So what do you need to start the project? No. Any inputs will be helpful. Or if you have written any ML program, for example, most likely you might have done Python scikit-learn based programs on training a machine learning model. So what is the process do you do? What are the steps that you will do? So I think I should have a lot of ML programs in my laptop. Let me see if I can get any one of them. Okay, so this is a code that we have written a few years back. And let's get into a regression or classification use case. Okay, so you can see this is our data. So mostly we'll ignore the user ID. So this is actually a classic ML fitting program data set. So if you see, we have a gender, age, and estimated salary of the person. And we have the data which is purchased, and we have zeros and ones. So based on the current knowledge, can you tell me which among these is what you might predict, and which among these inputs will you be using as input to an ML program? Most likely. Okay, so if there are not many answers, then probably I will actually start with the basics. Because the answers that I get is what I will understand as the ability of the current learning for the participant. So I'm expecting faster answers, and I want the session to be interactive. So else I will try to actually try to cover even the basics. If we answer a little faster, probably I'll skip the basics. That's the approach I will take. Okay, I didn't see any answer, so probably what I'll do is I'll actually proceed, and I'll try to cover some of the basics of ML, and then we will actually come back and we will discuss about this approach. So the normal machine learning approach we will discuss first, and then we will see the difference between machine learning and deep reinforcement learning, and after that we will probably get a deeper dive into reinforcement. That would be my approach, because ML will be the foundation. So if you ask me, what is the path to start with reinforcement learning? So in my personal knowledge, I will really consider only reinforcement learning as part of AI. So if you see, we even cover dedicated training programs on machine learning, deep learning, and AI. So this is the order in which we actually cover. So for example, we start with ML, which is machine learning, and then we get into deep learning, which is, we call it as DL, and then we finally end up reinforcement learning, which is AI. So AI, I will only consider reinforcement learning as part of AI, even though the broader terminology wise, if you see, people consider ML, DL RL, all of them as AI. But in my opinion, a true AI is only a reinforcement learning algorithm, can actually be a true artificial intelligence system, because these two are actually mostly trained by human labeled data, whereas this one actually learns on its own. So that's what we are going to see as the difference. So I'll try to probably give a initial 15-20 minutes introduction to the first two parts, and then we will get into the last part. So if you feel that my initial introduction is a little faster, you can let me know. I can slow down. The pacing of session purely, I'll keep it to the participants. I'll initially start with a little faster because the basics I want to cover faster so that we can spend more time on this. But in case if you feel that these parts are also important and you need some basics of it as well, then probably I'll slow down and cover things at a little more deeper level. Excuse me. So that will be my approach. So I'll proceed. So I'll skip a few slides and only focus on the important ones. So what is generally understood is data science professionals and data scientists are some of the highest paid individuals in the world. So that's how it was 10 years back, and that's how it is even today, and it will be the same for the next few years as well. And it will be the most attractive domain to work on in the software development. And this is about how much data can be stored on a single device and what is the cost of storage per in a device. So if you see, right now we can even have a 4 terabyte hard disk on a laptop. So that's a huge amount of data that you can accumulate on a single PC. And if you see, the cost of storage per GB has dropped dramatically. And cost of compute is also going down dramatically. So if you see 10 years back, we had mobile phones which had 700 megahertz compute capacity on our mobile phones, and it had one core. So right now we have octa-core processors which are in gigahertz level range of compute capacity. So what we can clearly see is there is a huge capacity increase. So which implies that even if you have several terabytes of data, even sometimes petabytes amount of data, you have computers today that can actually crunch all the data and do very sophisticated algorithms can be executed on such hardware. That's what you can understand. So in fact, in our premises, we have around 6 to 7 servers, each having roughly around 32 CPU cores with around 64 GB of RAM. And we train ML models on them, as well as we have planned to purchase some GPUs. But since we started moving away from ML and DL and we started moving into DevOps, we actually dropped the plan to actually buy GPUs. Okay, so even today, the fastest supercomputer in the world is still a human brain. So what we can understand is the cognitive capacity of the human brain to learn is far more superior than any of the world's best AI algorithm that is invented so far. But that will change in the near future, probably in the next 2-3 years. I'm expecting that computers will get very sophisticated learning that they will be able to surpass the learning capacity of a human. So the reason that the computers are finding it really difficult to learn data is mainly because of this. So structured data and unstructured or semi-structured data. So in my opinion, if you see, the main difference between machine learning and deep learning is, in the case of machine learning, we mostly only give structured data as input. So because those machine learning algorithms are very simple, and or they lack much higher complexity, and hence they cannot learn from unstructured data. So structured data are nothing but data that you can store in an SQL database or data that you can store in an Excel sheet. So those kinds of data are called as structured data. What is deep learning? So deep learning is capable of handling unstructured data. That's the major advantage between ML algorithms and deep learning algorithms. So in the case of unstructured data, we can discuss about images, audio, video, for example, even geographical data like satellite data, which is again kind of a three-dimensional structure of an image, etc. So these are the kind of data which are far more complex that the common machine learning algorithms cannot handle. So that's where we need deep learning. And reinforcement learning is an altogether different type of algorithm. We'll discuss about it once we finish the basic introduction. So what you can understand is the structured data we were able to conquer much earlier, even around 2005 to 2010 itself. The ML algorithms were quite popular, and they had been able to learn the patterns in the structured data. Whereas image processing, audio recognition had been quite a challenge for a very, very long time. And we were able to crack the understanding about those kinds of data only in the last 10 years with the advent of neural networks. So that's a major difference. When should you go for normal ML algorithm compared to when will you go for deep learning algorithms? So the difference is what type of input data you get for the challenge. So I'm skipping a lot of slides for lack of time, and also because I'm expecting that you already have some prior knowledge. So these are some of the important use cases for which we have already worked on ML algorithms in production, or these are systems that are already in production, which are actually being used globally. So today, with the pandemic in the past, but still during the pandemic times, we had a situation where there was lack of medical professionals. So where we have million patients and we have only 1,000 doctors. So the ratio is too huge, and we cannot have a doctor's attention for each and every patient always. So under that condition, AI became very, very important. So we wanted machines that can deliver food as well as medical supplies to the patients who were there in the hospital. So we can see that many hospitals were using robots to actually deliver the food as well as medicines, because people identified that getting closer to infected people are very high risk for the medical professionals. So in that case, we only used robots for delivery of food as per the prescription that is created by a doctor. But in the future, if another pandemic comes, even the prescription and diagnostics or diagnosis of the patient condition as well as prescription will all be generated by the robots. So we are moving into that kind of a direction right now. Okay, so medical field is one major place where AI, ML, deep learning, all of them are going to be used very, very heavily. But apart from that, you can see that pretty much AI and ML are going to be used in every industry vertical in the system here. So, for example, we have worked on retail as well as we have worked on healthcare, and we have also been trying to work on the transportation as well. Okay, so those are some of the domains where we have worked with the medical systems. And wearables is one major category of devices where ML and deep learning algorithms are going to be used as well. So we even have systems that can actually detect your thoughts. So what are the prerequisite knowledge that you will need or to master to actually work with ML? Of course, the math and theory, which are important, and then the algorithms that actually are built on the math that you already know, and then the engineering tools, the Python, the scikit-learn. For example, we have the platforms that are built on top of Python programming language, which are, for example, we have TensorFlow, Keras, and PyTorch, and so on. So those are some of the important tools that you might have to know. And then you also have to have domain expertise on the domain on which you're working. Okay, and you also have to have a very deep knowledge about data and data cleaning practices as well. So this single slide will give you mostly the knowledge that is necessary for you to get into the level of deep learning that we want. So machine learning is considered a place where the computer science, the math statistics, and the subject matter expert, all of that you should have as a single person. So that's when you can really become a data scientist, which is the unicorn that is in the center here. So now what I'll do is I'll actually only focus on the important aspects related to the data and data cleaning. And for example, when you start fitting the data, let me give you the process. So we'll start with machine learning, and then we will get into deep learning, and then we'll get into reinforcement learning eventually. So what is machine learning? So what you typically want to do, let me give you. So let me probably put that here. So you have some prior data, so which is usually called as existing historical data. So let me give you an example. Um, Today, fake news is being spread like wildfire. So what we want to do is, for example, we have Indian government. We want to monitor each and every social media network now. So what they want to do is they want to identify and block. So they have given an input requirement to, let's say, WhatsApp, and they want to block, for example, fake information. So, for example, there is a lot of fake information we would have already come across, and what the Indian government says is block all fake information as early as possible. So, this is the directive that is given. So now what you have is you have millions of messages, of which 10 messages are fake. So you have to detect it. So how do you do it? So for example, right now we are in 2022. So we have the data that was in the last 5 years. So for example, so from 2018 to 2021, we have the data of what is a real message and what is defined as a fake message. So you have the information here. So this information is actually called as your training data. So this is what is the answer I was looking for at the start of today's session. So before you can start any machine learning project, the prerequisite is you need the training data. So without the training data, you can neither start a machine learning project, nor can you start a deep learning project. So the prerequisite to start any ML project is actually the training data. And then once you have your training data, next step, what you will do is you will actually start cleaning the data. So your data cleaning is what you will do here. And in the data cleaning, you have to remove any data that may not be easier for the ML algorithm to understand. And you will also do data transformation. So data transformation might be very essential for your algorithm to properly give you valid output. So these two steps in general is called as data engineering. So data is a very big task, and we work heavily on the data engineering aspect of the ML projects as well. So let me give you what is the significance of data engineering. So, or data transformation. So let's take an important scenario where data engineering transformation can be really helpful. So for example, you have a bank loan processing system for which you want to predict who among the applicants who made the application to take a new loan will most likely be able to repay the loan. So you want to do prediction whether to give the loan to a person or not. So in that case, your input data is like this. So we have the following input about each and every person. So for each person, we have his age, we have his income, and we have his expenses and previous loan repayment, whether he paid it or not. So now you have the income and expense separately. So ideally, if you just give this much amount of information, it may not be easy for the ML algorithm to fit. So what you might want to do as a data engineer, so you have to calculate a few things that are important. So for example, the first thing that you will calculate, instead of just giving income and expenses, you can actually calculate something called as disposable income. So what is disposable income? So disposable income is nothing but the income minus expense. So for example, there is a person who has a salary of 20,000 and he spends only 5,000. So in that case, his disposable income becomes 15,000. But there is a person with 1 lakh as his salary, but he spends 95,000 of his salary in existing expenses. So in that case, his disposable income is much lesser. So what you can clearly say is these two individual data may be um, valuable independently, but combined together, they are much more valuable. So as a data engineer, you should be able to calculate such more useful transformed data that is important for ML algorithm to fit and give better results compared to just the raw data. So always for an uh, ML algorithm, you start with your raw data, and then you have your engineered data. So that's our objective. So whenever you work with ML algorithms, the most important aspect is you need to have properly engineered data. So that should have the maximum possibility of getting you the output that you want. That will be the next step that you will do. And finally, you start, excuse me, fitting your data. So you will do ML training on this data. So once you train your model, train your ML algorithm, what is the output of the training process? So what do you get at the end of the ML training? Any answers? So what you get is a trained model. So at the end of the training process, you get a trained model. So in real production scenarios, we don't just train one model, we'll train hundreds of models, and we'll train them with hundreds of engineered data. They will have different data sets with different transformations. And we'll try to validate which model gives the best accuracy. It's not just about accuracy, it's also about something called as an explainable model. So which means, can the model be interpreted for its outputs that it generates? So that is something that we will talk about. Okay, so coming back here, so such transformations are necessary. Coming back to the process of ML algorithms. So what do we do to train an ML model? So as I said, always the first step, the steps for training a model. So both machine learning and deep learning, these two are common. So the first step is always about collecting input data which is labeled. So labeling is nothing but prediction predicted data. So basically, for example, if you are doing fake news prediction, so in that case, which you have million messages or even billion messages. So among the billion messages, what are fake messages and what are real messages? You should have them as labeled data. So in this case, again, I asked this question at the start of today's session. So we have the past history of some luxury product that was purchased by some set of people. So in this case, whether the customer will buy the product or not, or has bought the product or not in the past history. So this purchased will actually be the label, and the input data will be the gender, age, and estimated salary. So usually when you have data, you will segregate them into two major parts. So one is the input data, which we call as the features, and then the output that you want to predict based on this input, which is called as label. So you have collecting input data which is labeled. That is the most important aspect, first step of any ML project. The second step will be data engineering of the raw data, and you get transformed data, and then on the transformed data, fit the various ML models, and then finally choose the best model which is explainable as per domain rules. So domain rules are nothing but, for example, if there is a bank, then the person who is working in the bank will actually have a lot more knowledge on what will make sense. So for example, the disposable income calculation that we said is actually a standard mechanism that is used in bank. So whichever properly data engineered model which gives the best output, we will get based on the domain experts who are going to validate the model as per the business rules. And finally, use the model for prediction in production. So you will productionize the model. So these are the general steps, the 5 steps that you will use to actually select the build a machine learning or a deep learning model. So, but the most important aspect here is that collecting input data and labeling them or creating a labeled data set, large data set, is what is a prerequisite to work with any ML model. So this is where the difference lies between the machine learning model and deep learning models. Sorry, the reinforcement learning compared with machine learning and deep learning. So then what is the difference and what is reinforcement learning? In the case of reinforcement learning, there is no input data. So which means there is no data collection possible, or is not feasible, or it's either you don't have any data or it is not feasible to collect data. And hence data engineering is a totally different aspect. So then how do you train a model with no data? So that is where reinforcement learning comes into picture. So for example, reinforcement learning will be the true essence of artificial intelligence. So why is that? Because the model learns on its own. It is kind of a self-supervised learning. So what is the process? And that is what we are going to see next. So let me see if there is any important aspect here. So I think I have skipped a lot of slides. So there are some data cleaning aspects that are given here. So inherently, your data might have some skews in any one direction, or it might have a lot of null values, and so on. So we typically remove them in the data cleaning process. And sometimes the data you get might be in different scales. So for example, time may not match, or if you have measurements coming from different countries and regions or from different users, they might give you the same information in different scales, like inches, centimeter, and millimeter. So if you don't properly clean this data and bring it to the common scale, it will have a big problem in your prediction. A lot of times in machine learning, what we understood was ML algorithms fail not because of the algorithm's inability to learn data, but mostly because the data is actually not properly in the right scale and right proper cleaning. So that's the reason. So error measurement and the other options are given here. So I think my topic is reinforcement learning. So I'm actually skipping all this underfitting and overfitting and all those aspects here. So probably I'll skip the rest of the presentation and we will get into reinforcement learning now. So from the reinforcement learning perspective, the first important aspect is there is no input data. So that's the major difference between ML and deep learning projects compared to reinforcement learning projects. So the reinforcement learning systems do not learn from past history. Instead, they generate their own data. So they're different from generative networks. That is different. But in a short while, you will understand how the reinforcement learning algorithm will generate its own data. I'll discuss about it with some examples and presentations. Okay, so let me give you some important use cases or kind of scenarios where reinforcement learning can be useful. So, for example, you have million data points. Let's say you have all chess games played by major players in the world, and for, let's say, for last 10 years. And probably with those games, you have, let's say, 1 million moves that are there. But in a real world scenario, even this 1 million data points, which is nothing but your labeled data. But to train an AI model properly, we might need even more than 10 to 100 million data points, which is nothing but labeled data. So what you can clearly see is the existing data is clearly not sufficient to train an AI model properly. That is one major reason why you cannot use the normal machine learning algorithm or deep learning algorithm to train such scenarios. That's the first part. And another reason why you cannot train an AI model is sometimes we do not have or not feasible to get data for prediction. So some of the examples are, for example, self-driving cars. So in a self-driving car, you cannot just go and create 1,000 accidents and identify how an accident can be done. So it is not possible. So what happens if a child comes in front of a car? So what happens if a person who did not see the car, he is talking on the phone and he comes in front of the car, and so on. So all those kinds of scenario, it is impossible to simulate 1,000 accident or 1,000,000 accident. That is impossible. So which means in real world, this kind of data cannot be created. It is infeasible because I cannot kill 1,000,000 people just to create a self-driving car algorithm. That's not possible. So these are some of the scenarios at which your reinforcement learning is the only solution, because a reinforcement learning algorithm can learn on its own, excuse me, without any prior data. So that is the first part. So under this condition, so first of all, I have to understand, without data, how can you train a model? That is the first question. So that is the first answer I will try to give here. So how will I train an algorithm or a model without any data? So for that, what we typically do is we create a simulated environment. So what we do is we create a first a simulated environment. So in reinforcement learning terms or in AI terms, we just simply call this as an environment. So in this, we will actually simulate all the physical properties that you need to your model to be properly trained on. You actually simulate all of them. So for example, if you're training a robot that is going to learn to walk, so in that case, you will simulate even gravity, you will simulate the forces, you will simulate when will the robot brake, the forces, all that information will be given in the simulated environment. So those will be there in the definition of the environment first. And once the simulated environment is first created, what you will do is you will actually put your agent here. So this component here is actually the learning agent. So in short, we call it as an agent. So this is your learning agent. So what you're doing is you're introducing a learning agent inside your environment. And then what you will do is you will give a set of commands to the agent. So for example, these are either the agent can move towards the, let me put those in a different color to highlight it. So if there is a car, either the car can move forward, or it can move to the left, or it can move to the right, or it can move in the backward direction. So these are the four possible outcomes. So you define the action space. So this is called as action space. So what is an action space? Action space is nothing but the list of operations that an agent can take in an environment. So in this case, forward, left, right, and back. So the action space, we have 4 actions that the agent can take in this environment. So you define your environment first, then you define your agent, and then you define your action space. So now, finally, the only pending part is actually the last part, which is actually rewards. So what is a reward? Let me give you with an example. So for example, hit obstacle. If you hit an obstacle, then you get negative reward. Whereas if you move towards your target, so you define a positive reward. So for example, negative reward, if you hit an obstacle, you get -1000 because it is like an accident. Whereas if you move towards your target, you are going to get a positive reward. So for example, a positive of +10. Whereas if you move away from target, in that case, you will get a negative reward. So for example, -10. So this is what reinforcement learning algorithm is all about. So for example, you have a self-driving car that should navigate through the city, and it should automatically take you from your home to your college or to your office. So in that case, you typically book an Ola, and there is a driver who is actually going to come and pick you up, and he knows to navigate through the city, and he takes you to that destination. But in a self-driving car, we want all the work that is done by the driver to be taken by the agent. So in that case, the self-driving car agent will become the learning algorithm. So for example, your target is here, and your starting point, for example, is here. And there are some obstacles on the way. So now what happens is the agent should learn to move in this direction. So he should go from here, and then he should take this path, and then finally reach this destination. So now from here, if the self-driving car moves towards away from the target in the wrong direction, it will get a negative reward. That's the idea. And if it moves towards the correct direction, in moving towards the actual path, it will get a positive reward. Whereas if it hit, let's say, some obstacle in between, for example, there is a person standing here, and if it hits that person, or if it hits another car, in that case, it's a negative reward. So notice that there is a big difference between the normal positive and negative rewards compared to hitting an obstacle. Because ideally, you don't want your car to make any accidents. So if there are any operations that make huge negative impact, then always try to give a very, very high reward to the agent, so that what happens is it will actually be totally avoiding to take such an action. So this is like uh, the way we teach our students. So for example, you ask your student to learn your do some homework, and he does it, then probably you give him some marks, which is positive marks. But if he doesn't do the homework, then probably you give him 0, so which is nothing but the reward. So sometimes you also give an imposition. In that case, it's a huge negative reward. So that is how it works. So now what happens is every day when the student start getting the more harder the negative reward is, the more stringent the student will try to comply to the rules. So for example, if the student completes this assignment, to give him +10. If he doesn't complete, if you just give him 0, let's say out of 100 students, probably 20 students complete the assignment, whereas 80 students do not complete the assignment, because the risk of not completing the assignment is small. But if I give him -10, then instead of probably 20 students completing, now we will see a jump. So for example, at least 50% of the students might complete the assignment, because to avoid the negative ranking. But if you give -100, then probably you can see that 70% of the students might complete. So which means the larger the risk or larger negative rewards you give to a particular person, then there is a higher chance that he will try to move towards your expected intended direction. So that's the reason you actually give different levels of rewards depending on what you want your agent to really not never to do and what you want your agent to do always. So based on that, you will actually have different levels of rewards. So now coming back to reinforcement learning. So reinforcement learning is always about an agent learning in an environment. So that's what is the reinforcement learning. So you can clearly see that the agent, by taking some random actions inside its environment, using its action space, it can take any of these actions. What you do is you start giving it some rewards. Based on the rewards, it will start learning to do what you want it to do, and it will stop doing what you don't want it to do. So that's the idea. So for example, every day you come to college and you ask your students to do the assignment, and only some of them do it. So now what happens is, the higher the risk, then the higher the negativity of the reward, there will be more students who will do what you want to do, right? So that is the way the AI algorithm also works. So the AI algorithm is nothing but a reinforcement learning algorithm is nothing but an agent put in an environment, has an action space, and it can take random actions, and based on the random actions you train an AI model. And to train the AI model, you need a set of rewards. So these rewards should be predefined and predetermined, and how well you set the rewards will actually make the agent learn even faster. So reward is a very important aspect of the overall learning process. So finally, so this is what is reinforcement learning. So agent learning to take correct actions in environment is what is reinforcement learning. So how exactly it is done is a lot more complex than what it looks like here, because the real essence of learning, if you see, is much more difficult to understand, and those concepts I will explain next. But by now, I will give a summary of what we have discussed in the last 50 minutes, roughly. So we have discussed that machine learning algorithms train on structured data. Deep learning algorithms train on much more complex unstructured data, which are much more larger in action space, in size. And deep learning algorithms are always neural networks. Okay, so the commonality between machine learning and deep learning is you have a set of labeled data on which you train your model. So that's typically how always a machine learning or a deep learning model learns. Whereas in the case of reinforcement learning, either you don't have sufficient data which is sufficient enough to train the model, or it is impossible to collect or create such a data, because I cannot go and create a million accidents for the algorithm to learn. So in that case, I cannot create real data. So the only way is I have to create a simulated environment and train my model under various different simulated conditions. So that is where the reinforcement learning comes into picture. So the reinforcement learning is not going to be given any input data at all. And that is the real reason why reinforcement learning is of very, very significant importance. And people who can work on reinforcement learning will have amazing pay scales. There are even people who are working in India who get $1 million salary, which means roughly around 7 to 8 crores per year, who are not CEOs. They are still data scientists, and they can earn so much more because of the importance of such kind of algorithms. Okay, so now coming back, so reinforcement learning, we'll get into the technical aspects, but hopefully it is clear now. So the most important aspect of reinforcement learning is you don't have any input data. So the agent will generate the data during the learning process. For that, you created a simulated environment, and inside that environment, you create the all the basic physics or whatever it is necessary. So you put all those rules in your environment, and then you introduce an agent in the environment, and the agent will have an action space. And by taking an action, the agent will either get a positive or a negative reward. And depending on the reward, there will be an AI algorithm that will be inside the agent that will actually start learning to take actions that actually gives positive reward, and slowly it will stop doing taking actions that will give negative reward. So that is the overall idea behind reinforcement learning. If you have any questions so far on whatever we have discussed, please let me know. I'll probably wait for a minute to see if there are any questions. Let me close this file. So we can see that reinforcement learning will be the toughest type of learning algorithms to implement, because there is no input data and it is not easy to make the uh, agent learn, because the rewards looks very simple here, but it is not easy to actually apply this reward on the model for taking a particular action. So we will see that in a short while why there is the. Any questions? Fine. I don't see any questions. I have an exclusive document on reinforcement learning. I will try to cover that now. Okay. So I'll start introducing a simple scenario with which we will learn what are the complexities of AI training. So I didn't discuss about state yet, but I discussed about action, I discussed about reward, and I did not discuss about discount yet. So we will understand what is the discount and why it is important. But I think I can try to give some information on it straight away. There are several reasons why an AI algorithm cannot be trained easily. So let me give you an example. So for example, I have a chessboard and I'm going to make an AI learn to play chess. That's my AI algorithm's intention. So let's consider that I have moved a pawn. So for example, there was a pawn here, and from here I moved it to here. And you can see that by moving the pawn, there is a move 1. M1 is the move 1, where I moved my pawn from, or I'll call it as action 1. So action 1 is nothing but the first action where I moved the pawn from certain location to certain other location. So for example, we'll call this as B2, which is here, and this is B3. So this is B4 and so on. So now what happens is I moved the pawn from the B2 position to B3 position. So now the pawn is not here, it has got moved to here. So in the next step, what I did was I again moved the pawn from this position to the next position here in the chessboard. Again, I moved it here. So far I have taken two actions and I did not cut the pawn of my opponent, neither did I lose my pawn. So for these two actions, so for example, this is A2. For example, the A1 action is moving the pawn from B2 to B3. Probably the action 2, the second action that I took was moving the pawn from B3 to probably B4. So if you see, so for these two steps that the agent has taken, I cannot give him any rewards, because neither did I lose that coin, nor did I cut my opponent's coin. So for example, if you lose a pawn, so in that case, I will give a -10 reward. Whereas if I cut my opponent's pawn, so in that case, I'll give a positive reward. But neither of these two outcomes has happened. So these are the rewards I give to my pawn. But you can see that neither of these two has happened yet. So hence, I cannot give any rewards for these two actions. That is the problem. So in the case of reinforcement learning, the biggest challenge is for every action that you take, you cannot give a reward to your agent. So that is the main problem that you will face. Let's say you take another action where you move your pawn from here to the next position again. So now in this position, after moving, for example, what happened was your pawn was cut by your opponent. So in this case, this is a wrong move. For example, I lost my pawn. So now if you see, there is a third action that has happened. So where I have taken action 3, where I moved the pawn from b4 to b5. So now the challenge is this. So even though only the third action that I took, the a3, actually resulted in a negative reward, but I cannot just simply apply the entire negative reward only to this action, because even these two actions contributed to that particular outcome of losing a pawn. So which means this negative reward that is given to action 3 is not just applicable to action 3, but it is also applicable to the series of all the actions that I have taken to eventually lose the pawn. I have to actually now give the negative reward to all these 3 actions. So this is the challenge of reinforcement learning. So how do you distribute your loss or of pawn, which results in a negative reward? How do I put that negative reward to all these actions? So for example, if you don't have a pawn anywhere here, then moving your pawn from the first step should actually get me much lesser risk. Whereas if I move from here to here, I get a higher risk because I'm going closer to my opponent. But if I go to the closest possible position, then that gives me the highest risk. So then what you do is you do something called as redistribution of your risk and redistribution of your reward. So for example, this gives me the maximum vulnerability of losing my pawn. This gives me much lesser vulnerability. This gives me even lesser vulnerability. So which means moving the pawn from here to here, I want to give much lesser negative reward compared to moving my pawn from here to here. So how do I do it? So basically, this is called as discount factor. So you give the entire -10 negative reward for moving for the action, making the action A3. Whereas this action A2 also contributed in losing my pawn. So in that case, I will put a negative reward of, let's say, for 20%. So then what happens is, if I reduce 20% from -10, it implies that I will get -8. So which means I will apply a -8 as a negative reward for taking the action A2, which is moving from B3 to B4. And apply the same 20% rule, then removing again another 20%, probably I'll give a -6 of moving my pawn from here to here. So this is how you do it. So it looks a little simpler to actually back propagate this error from the action that resulted in a real negative reward to all the other actions that were taken prior to it to actually give me the final negative reward. So I can actually put a discount factor. So this concept is called as applying a discount on the previous action is actually called as the discount factor. So this discount factor is important. That way, the point at which the agent is at the highest vulnerable stage, you're given the maximum negativity or negative reward at that position. Whereas the position prior to it still have to get a negative reward, but they are not as vulnerable as you are here. So in that case, you give much lower vulnerable negative rewards to it. So this process is actually called as queue learning. So what you have to do is every action you do, you actually put it into a queue. So then what you do is you enqueue every action that you do. And then what you do is when you finally get a reward, you apply that reward with a discount factor to all the previous actions that has resulted in the reward. So what you do, you record your actions. So recording your actions or nothing but saving or recording your actions in a queue. So hence this process is called as queue learning. So which means you take a series of actions and each and every action that was taken, you put it into a queue. and finally, eventually, you get a positive or a negative reward. And then what you do is you take each and every step in the previous stage of the overall learning process, and you apply that cue to the previous actions with a negative or positive reward that you got. So for example, instead of losing a pawn, if I have cut the pawn, I would have given a positive reward. So in that case, this will get the highest positive reward, this will get the next lowest positive reward, this will get even lesser, this will get even lesser. But eventually, instead of negative 10, you will get positive 10. And instead of negative 8, you will get positive 8, and so on. So that's how the process works. Are we clear so far? Any questions on the Q learning and also on the concept of discount factor? So the discount factor should allow you to not take actions that makes you go into a dangerous situation. So the higher the vulnerability or the higher the risk, it should get a much higher negative risk. So for example, if your student does not do a single assignment, so he'll get 0. If he does not do 3 assignments consecutively, then he will get -10. If he did not do even a single assignment in an entire semester, he gets suspended. So kind of you can see that the more and more negativity that you add to the student, the lesser and lesser likely that he will do something really bad. So we already have that. So these are all real world situations. We are trying to apply the same logic to an agent that is there in a reinforcement learning environment. So what are the things that I have highlighted, and what is that is missing? So finally, the only information that I did not discuss so far is actually the position. So you can see that B2 is the current position and B3 is the target position. So what is your current position of the pawn? So that is called a state. The state is nothing but your current position. So each and every position in the chessboard is actually has a unique state, or you know the position. So if you can track it, it becomes a state. So if you move, for example, very close to the enemy boundary, then where you take that action also has a significance. So for example, you are very close to your position and you move forward, it's not going to be that risky. But you are very close to your opponent's position and you move close further, it is a much more riskier position. So if you have to take proper cognizance of the risk that is involved, you should always know your state. So a state is always your current position. And what is the action? And your action will move you to a different state. So for example, your current state is B2, and you, by taking action A1, you moved into B3 state, which is nothing but you moved into a new state. So by taking each and every action, you move from one state to the other. So I think I have now discussed mostly all the prerequisite information that you need to understand about AI and reinforcement learning. So reinforcement learning is nothing but where you have an learning environment that is created which as a simulated environment, and you put an agent into it, and that agent will have a current state, and he has an action space in which he can take an action, and by taking an action he will get a reward, and but not every action will produce a reward. So if a bunch or series or queue of actions has finally resulted in a reward, then how do you distribute the reward in the path that the agent has taken? So for that, we need a discount factor. So these are the 4 symbols that are given here. So the state is represented as S, and we will be creating an equation with this particular set of data. Because always when you want something to learn on its own, you need an algorithm or you need an equation. And that's what is the equation that we're going to form. And these are the symbols that we will use. So current state is represented as S. The action that is taken by the agent is A. And then the reward that is finally received for that action, taking that action or a set of actions, is R. And you have a discount factor to distribute the reward to the previous actions that was taken, which finally resulted in a larger reward. So this is the overall idea. So for discussing about this final state and trying to understand the importance of discount factor and so on, so we are going to discuss about an simulated environment here. So for example, this robot here is actually like an agent, and the agent is supposed to move from the starting point, which is here. You can see that here. So let me try to put that here. So for example, I'll take a screenshot of it. So the agent's starting position will be here. This is the agent, and that agent should eventually move to that target here. So this is our target. So he should move here. So if he moves here, he'll get a positive reward, let's say of 10. Whereas if he moves into the fire pit, for example, it could be a no entry or it could be an accident prone zone, whatever it is in real world. So if you want certain actions to be always avoided by an agent, you put a negative reward here, maybe even much higher negative reward. So for example, even if you don't reach your destination, you still should not create an accident. So in that case, creating an accident should be having a huge negative reward, whereas finally reaching the target should be a positive reward. And in between, you have an obstacle that you cannot touch. So what do you do? So you have to take a path like this. Either you can take this path or you can take this path. So you have two paths here. So what I'll do is I'll actually put the information in probably a new paint. Okay, so if you start from here, can you tell me by looking at this particular, so your starting position is here. So you can move in this direction to reach the target. So I'll call this actions path as path 1, and I'll give another path where I can move in this direction. So can you tell me which path among the two is actually more preferred for the agent? So which is the path that you should prefer, and what is the path that you should not prefer, and why?
So P2.
So P2, should I prefer or should I not prefer? Uh, yeah, thank you for answering, but I want further clarity. Like, are you saying that P1 should be preferred or P2 should be preferred? Is your answer? So let me check the chat, because sometimes people can use the chat as well to answer. Okay, so any answers? What should be preferred? So there are a lot of scenarios in real world which are like this. So you should be able to easily judge. So in my opinion, P1 is actually much more preferable, whereas P2 is actually a risky option. Why? Because in the path to P2, if you see, there's a good chance that I might end up falling here. But in the case of path P1, there is no chance of, or at least there is much lesser chance of falling into the fire pit. So in this case, if I have to fall into the fire pit, I have to come here, and I have to go here, and I have to fall here. So if you see, P2 is much more riskier compared to P1. That is one reason. Another reason is from the risk perspective. Another reason is which is more efficient. If you see, how many actions do I take to reach the target? So for example, I have 1, 2, 3, 4, and fifth action, I'm in my target. So if you take the number of steps that is necessary in the other path, if you see 1, 2, 3, 4, and 5. So in this case, both paths look very similar in their distance. So distance wise, maybe it is not much different, but from the risk perspective, if you see, this is much more riskier compared to the other path. So that is the reason I would really suggest to go for P1 compared to P2. So now, from our knowledge as a human being, we have a lot of cognitive thinking ability. So from our thinking ability, we can identify that P1 is actually preferable and less risky and safe compared to P2. So this is something that we can understand from mathematical perspective. So how do I represent it mathematically so that I can make the agent learn mathematically through numbers, through risks and rewards, that agent should try to learn to take the P1 path and should always try to avoid the P2 path. So how do I make it learn it? So that's what is we are going to see in the reinforcement learning use case here. So this is what we have. So the green target, if you reach, you get a positive reward of +1. If you fall into the fire pit, you get a negative reward. So these are the two things that we have. So based on that, for example, if I reach, for example, if I start here, let me put another paint here. So what I do is, if you see that I told you that by reaching, so the final rewards are, if I reach this position, I'll get a +1. Let me put that here. Whereas if I reach this position, I'll get a -1 here. And my starting position is this. I start from here. Then what happens is, so you took the P1 path and you reached your destination. So since you reach the destination, what you do is you start putting your rewards. So since you got the +1 reward for reaching this position finally, the path you took is this. So you have to put the +1 reward here. So if you don't give a discount factor, what happens is you will have the +1 reward here as well. So what you do is you know the sequence of or the queue of operations actions that you have done, and you put the reward for each and every one of these actions that was taken. So you can see that you have taken this path. So for if I move from this position to this position, I can give up a plus reward. So +1. So that way what happens is the agent will always try to prefer to move in this direction. Right? So that's what we have done. So that is the path that we have given. So we start from this position, and then we give the same +1 reward for each and every action that it has taken. So what it will do is it will get a confusion. So now if, for example, if I am at this position, so at this state, if you see, if I have given my rewards in this direction, so what happens is if I from here, if I move from this state to this state, I get a positive reward of +1. Whereas if I move from here to here, if you see, I will also get the same +1. But if I have to reach this position, then what do you need? So you should always move in this direction, and you should not move in this direction. But if you have given by taking this path, you have given +1 reward, which is the final reward that you got. If you put the same reward for each and every step that was taken here, there is a problem. So in the intermediate stage, now if I'm here, if I go in this direction, also I'll get the same +1 reward. If I go in this direction, also I'll get the same +1 reward. So in this case, the agent will not take the right action. So if I want to enforce the right action, then I don't want to give equal rewards for each and every action that was taken by the agent. That's an important part. Okay, so that is the first reason why you should not give directly the original reward. You should not give the same reward throughout the path, because in between the path, if the agent is in the middle, then it might get confused in going in the right direction. So for example, if the agent, if it goes here, it doesn't know the reward because it has never taken it, but by reaching, it was able to reach that final target in this path, so it will actually take this path. But if it goes here, it doesn't know the reward, so always it will take this path. So this is again a problem which we will see later. But yeah, so it has taken a path and it has gone to some destination, and the destination was good, so it got a good reward for each and every action that it has taken to reach that target. It has actually been given a positive reward. But at a particular position, if you see, there are problems. So if you give equal reward for each and every step, what happens is it might not know which step, or it can take both these actions equally. So if you give equal rewards, then what happens is in the middle of the path, it doesn't know in which direction it has to go, because in any direction it will get the same reward, but eventually it will not reach the destination. So that's the reason we don't want to give equal reward for each and every action taken by the agent to reach the position. And that's what is given here. So if I give +1 reward for each and every operation, so it leads to confusion to the agent, because when the agent is at a particular state, what happens is by moving in the opposite direction, if it gets the same reward, then what happens is it will not reach the destination. So repeatability becomes a problem. So instead, what we do is we create something called as a discount factor. So now what happens is we give a discount here. So the discount factor is 0.9. So in this case, for example, from this position, if I reach the target, I got a +1. So I think what I'll do is I'll try to explain it with this particular same action that I have taken earlier. So let me go back to this particular diagram. I'll put that here. So I'll explain it again. So we have, for example, +1 here if I reach there, and I have a -1 reward for reaching here. So from this position to here, if I take, then I'm going to give the agent +1 reward, which is nothing but the final reward that I got. I'm saying I'm going to put that reward in this step here. But the previous step, I don't want to give +9. So instead, what I'll do is I'll give the reward for the previous step should be equal to reward on the current step into a discount factor. I'll call it SDF. In this case, for example, so the reward for, so I'll keep this state as S1 and S2. So now what happens is at state S1, moving forward is the action. So by taking the action A1, what happened was I got a reward of +1. So I'm saying that for action A1 taken at state S1, I'm going to give the reward of 1. So whereas the reward for taking an action of moving forward from S2 to S1. So what is the reward? I don't want to give this +1 here. So instead, what I'll do is the reward for the S2 position should be equal to reward for at the S1 position multiplied by the discount factor. So in this case, reward at S2 position will become 1 into 0.9. So in this case, reward at S2 position will become 0.9. So this is how you calculate it. So now what happens is, by applying this formula, the reward that the agent should be given for being here and moving forward should be 0.9. So similarly, this is S3, and at the S3 position, it should again move in this direction. So if it moves from here to here, what is the discount I should apply here? In that case, if you apply the same logic, what you will get is you will get 0.9 into 0.9. So I think I've given the filled up values here. You can see that here. So from 1 to 0.9 and from 0.9 to 0.81, 0.81 to 0.73. Maybe mathematically, I'm not sure if that is correct, but this is how we calculate it. Okay, so now what happens is we apply a discount factor of 90%. So what happens is, so you reduce 0.1% of your data to the previous step. So this is how it works. I think it's correct. Okay, so this is the reward we have here. So this way, what happens is at any given position, now there is a clarity. So if I start moving in this direction, I'll get the, I'll be able to reach the target. So now what happens is we are overcoming that confusion that we would have had earlier. So for example, if my agent is again at this position, you can see that if it moves in this opposite direction, and if it moves in this direction, you can see the difference. So if it moves in this direction, it gets a lesser reward. Whereas if it moves in this direction, it gets more higher reward. So always the agent will try to take the higher reward action. So action that will result in a higher reward. So that way what happens is the agent does not have any confusion in moving to the target. By applying a discount factor, we are ensuring that the agent will always take the right action throughout its action space to reach the target. So hope it is clear now the importance of the discount factor in the overall formula. So now if you see, I have to explain this particular formula. So what I'll do is I'll again put that into a pane so that I can explain it a little earlier. So if you remember, I told you that this reward R is actually reward. So what is R of S of A? So reward for taking action A at state S. So this is what is R of S of A. So which is because, so at each state, or your reward might be different for taking the same action. So for example, this is important because you have to know what is your current state. So if I'm here, moving here forward is actually supposed to give me a positive reward. But if I am here And if I take the same action, which is moving forward, you can see that I'm going to fall into the fire pit. So, which means not at all states, you will not get the same reward for taking the same step. So, for example, um, if if my current state is S1 here and S2 here, so your action is actually move right. So that's my action. So if you see moving right at state of S1 will give me a positive reward, whereas taking the same action, moving right at state S2 will give me a negative reward. So that's the reason rewards will be different for different states for taking the same action. So that's the reason when we calculate the reward, we calculate the reward for taking action A at a particular state. So you need to consider both the state and the action. So now if you see, what is this gamma here? So the gamma here is nothing but the discount factor. And what is this S dash here? S dash here is nothing but the action that was taken in the next step. So what I have showed you here in short is actually what is given properly here. So if I try to probably put that information here, maybe it will actually makes little more sense. Let me see if I can put that here. Yeah. So then how do I understand this? So the V of S is nothing but the max of taking that action. So the first is V of S dash. So I'm not sure if I have that symbol here, so I'll put that here. So V of S dash. So what is this? So that is nothing but reward on the previous step. So reward at S. So that is what is the point. So basically, for example, this one here. So how do I calculate this 0.9? So the 0.9 here is actually the reward at S2. Okay, so the S dash represents, so your current state is here. So I'll put that in the, so for example, if I have, let's say 0.81 here, and I want to calculate what will be the reward at S4, which I don't know yet. So for example, the agent has moved forward from here to here in order to reach the final destination. So now I want to know what is the reward I can give for taking action A, which was done, which is actually to move top. So which means moving upwards. So for moving in this direction, that is the action that was taken. So what should be the reward I should get? Considering that I've got a reward of 0.81 here, in that case, what happens is I have to calculate the reward for the current position. So the reward for current position is what we are trying to get here. So the maximum of reward of state of SA, so plus a discount factor on the previous step. So which means the 0.81 plus the current reward. So the current state reward, we don't have anything, whereas the reward of the previous state is 0.81. So in that case, what we do is we take this 0.81, multiply by this discount factor of 0.9. So he get for the current state, you get the value of 0.72, I think, as per this calculation here. Yeah, 73, sorry. So as per this calculation, if you apply this, what happens is for each and every previous stage, you will be able to get the reward calculation. So the same way, if you apply that here, you can see that you will be able to reach the target. And this is how the rewards are applied, or the final rewards you get by applying this formula. So probably I'll put that formula along with the rewards that are obtained side by side, so it becomes a little more clear. So for example, this is the current reward for taking the action at a particular position. So the reward that was obtained for reaching this particular position, and so based on that, I will put the reward for this previous position. So now what happens is, by looking at this, what happens is, if the agent is here, what it can do is it can move in either of these two positions. Both paths are now equally rewarding. So from here again, it can go to here, and from here to here, and finally here to here. So the same way it can go from here to here, here to here, and here to here. But as I told you, so both path becomes equally rewarding, because you can see that the action, it can take either path 1 or path 2, and both looks equally promising. But we know that as a human being, we know that this path is risky and this path is actually more safer. So how do I represent it? So this equation will not give me that safer path, because this equation can give me both paths as an equally viable option, which I don't want. So which means if I want my agent to always take this path and always avoid this path, so in that case, what I want it to do is, if it moves in this direction, it should get less reward. If it moves in this direction, it should give more reward. So for example, if it moves here, instead of 0.73, for example, if I keep the reward as, for example, equal to 0.5. So now what happens is, the agent will think now. So I'll try to increase the font size a bit, probably 22. Yeah. So here, if you see, now what happens is, at this position, if the reward is 0.5, what happens is, by taking this action, which is moving top from this current state, it will get a reward of 0.73. Whereas if it moves towards the right, by taking that another action, it will get a lesser reward. So that way, what happens is, if the reward is lesser in a particular direction, the agent will try to not take that action. So that way, I can make it prefer this path by reducing the reward in this path. So that is my ultimate objective. So reduce the reward in this path so that the agent will avoid taking this path, whereas maximize the reward for this path. That way, the agent will always prefer the lesser riskier path. So that's my objective. So let's see what is the change that is necessary in this equation to actually get a different reward for this path. So that's going to be our next task. Our path is right now, if you see, as per this particular rewards strategy, that scores that we have got here. So the agent will always move from lower, from current position. It will always try to take an action that gives a higher reward. So that way, by taking this, if you put arrows correspondingly, or the actions that can be preferred by the agent, you can see these are the paths that the agent will try to take. Next is, if you see, there are some search. Okay. So there are some theoretical information that is given. So what we want to do is, sometimes what happens is, once you discover a single path, that is not always the best path. So let me give you an example here. So you have, let's say, Coimbatore, and we have Ukadam here, and we have, for example, Gandhipuram at the center of this particular city, and you have Madavalli, which is at the north, and probably we have Saravanampatti. I'm trying to take some use case that is easier for us to understand. Okay, so now let's say we have an agent which is supposed to be moving from one place to the other. So let me put the boxes very similar to how we have seen in our previous exercise. So this is our path. So now if you see, there is a self-driving car that I invent myself, and it is at Badavalli right now. So what I want the agent to do is, I want the agent to move in this direction and reach Saravanampatti. That's my objective. But instead, what happens is, let's say the agent started taking some random action. Then what happens is, from Madavalli, it went to some other place, and from there, it went to, for example, another place, and it went to Gandhipuram, and from Gandhipuram, it went to, for example, maybe Hope College, and then finally, it went to Saravanampatti. So you can see that this path will be very, very, very long. But what happens is, it was actually able to reach Saravanampatti eventually. So then what happens is, we get a +1 for reaching here, which means from Hope College reaching Saravanampatti, it will get a +1. And from Gandhipuram to reach Saravanampatti, it will get 0.9. And from somewhere else, probably it will get 0.81. And you can see that it will get 0.73 and probably 0.6. So now what happens is, it knows that randomly it has, you never navigated in this city. So what happened was, you asked some people, and then, or you just randomly started taking some rights and lefts, and you eventually reached here. So this is the path you have taken. So now next time when you travel, what happens is, you will never take this path, because this path I don't know the reward, but for this path I know the reward. So since it gives me a route to reach the destination, I know that I can reach my destination of Saranapati through this path. What I will do is I will never take this path at all. So which means this is never going to explore new path. So if I've already known a reward for taking a particular action, I will all further operations, I will only take that path. I will never try to learn a new path. So this is actually going to be very, very inefficient because let's say you create 100 simulations and on the third attempt, the agent was able to reach the target, but it took a very inefficient path, but it was still able to reach the path. For all the previous actions, it was not able to reach, so it will not take that further path again. So now what happens is all further actions, the rest of the 97 times, it will use the same path. Because once you know the reward for a particular path, you will never take any other path because you know the path and you have a reward. But from here to here, I don't get a reward, so I will not do it. So this is what will happen. So if you apply the logic that we have showed earlier, what happens is once an agent knows what is the one of the ways to reach the destination, it will never reach, it will never take any other path, and it will always use the same path. So that is called as deterministic search. So which means you know the path and you have reached it and you know the reward for a particular action. So you will always take the same action. So this is again applicable to humans as well. So for example, there is a person who is working in a particular professional. And so you know that the rewards of continuing the same thing is lesser, but he'll keep doing it. But he will never take an alternative path because when you don't know the reward for taking that particular path, so it is considered as too risky. So for example, let's say there is a person who is working as let's say as a tester, and he gets lesser salary, and he can actually learn something new and become a developer, but the risks are high. So for example, he has to quit his tester job and then he has to learn the programming, and then he has to apply for the developer position, and he have to join the job to get a higher paying salary. But the problem is when I stop my current job, it is a big risk, right? So which means what happens is people do not take path that actually leads to a higher risk, and they will always keep doing the same work. Even in the long term, it is much lesser rewarding. They will continue the same path. The same thing happens here in AI as well. But what happens is once you learn an inefficient way to reach the target, you will never learn new other ways. So that is what happens, and that will significantly reduce the overall efficiency of the final learning that you get from this particular approach. So what do we do? So in that case, what we do is, in the case of deterministic search, you actually always take the same operation which is given here. I think that is put here. So when you know the reward for taking a particular action in my previous stage, I will always take 100% always the same path. I will never change my direction. But if you want your AI algorithm to explore more about unknown paths, then what happens is there are people who always are willing to go into a path that they do not know, and they are willing to get newer rewards either, and the rewards can be both positive and negative, but they don't care about the reward. They still want to explore. So in that case, what happens is I can randomly take an action. But if I randomly take an action, so for example, if I'm totally random, for one time I might take in this direction, next time I might take in this direction, and next time I might take in this direction. So now if you see, there is a big problem. So if I give equal importance to all the paths, then what happens is there is a 33% chance that I will fall into this fire pit. That's really dangerous, because by more introducing 100% randomness, what happens is the risks are high. So how do I control it? So in that case, what you do is you introduce a randomness, but the probability of taking that random action is actually supposed to be lesser. So how do you introduce it? So it's quite simple. So what you do is 80% of the time, which means majority of the time, from here you will always move in this direction. So this is 80% of the time. So which means you know that there is a low risk and highly rewarding outcome. So then you take that operation majority of the times. and 10% of the time take this action, and 10% of the time take this action. So which means there is small fraction of your overall. So for example, if I simulate my AI algorithm 100 times, 80% of the time it will actually take the same action that it has taken previously to reach the target. But 10% of the time, it will also explore other options. So this process is called as exploitation versus exploration. So let me explain the difference. So if 100% of the time, if I always take the same action that has actually given me a positive reward eventually at the end, then that will be only purely exploitation and there is no exploration, which means you never explore any new possible outcomes. Whereas exploration means I always take actions that I never took before. That is exploration. But if you keep taking always random actions and you take actions that never was done before, then what happens is more likely you will actually result in a failure condition, because you never tasted success, or you never reach the target by taking that path. Then you take more such path, then there is more failures that you will face. So then what you do is you want to have a balance between exploration and exploitation. So how do you do it? So basically, majority of the times take the same path that actually resulted in a previous success. But 10% of the time, 20% of the time, take new paths that you never have taken earlier. So which means try to introduce some randomness in the path that you have taken. So that way what happens is there is a good likely chance that you will also do exploration and exploitation simultaneously. Are we clear with the difference between exploration and exploitation? Any questions? Any questions? I didn't see any questions, so I'll move on. Okay, so that is what is Markov process. So the Markov process says that if there is any unknown path that you have to explore for an agent in a new environment that is never explored, then always there should be some randomness. And that process is called Markov decision process. So the Markov decision process is a mathematical way of introducing some randomness in such a way that it will maximize the exploitation by majorly 80% of the time taking known actions that has previously given a positive reward, and 20% of the time, or some small fraction of your overall action space, you will introduce some randomness, so that what happens is you will also take some random actions that are totally never taken before. So that way you will do some exploration as well. So for example, you go to a new city and you don't know anything surrounding, and you want to do some of things. For example, you want to buy some grocery and you don't know where your grocery shop is. And now what you do is there are different paths that you can take. Some path might be longer, some path might be shorter, some path may never lead you to the grocery store. That is fine. But you should learn to take every path. So that way what happens is you will be able to reach some path. So for example, this is what I want to say. So you are at one position, and now what happens is there are some different paths here. So for example, there is one road which is here. From here it will not lead you to the destination, but there is another path that might actually able to lead you to the destination. But it is not always that you only have one destination. So you might have more than one destination. So for example, there could be a shop here. So what you do is if you go in this path and you reached a shop in this path. So now what happens is, so in this path, I was actually able to reach a grocery store. So that happened a couple of days back. And I was actually able to find a grocery shop. So the distance is, let's say, for this path is 2 kilometers. But if I always take this path, I will never know that there is another grocery shop that is in another path. So probably this path is even shorter. So it is just around maybe 0.5 or 0.4 kilometer. So you can see that by doing always exploitation, so which means once you reach your destination in a particular path, you never are going to explore any further path. So in that case, what happens is we are never going to exploit it. So this is like, for example, you go to a particular hotel, you take food there and it was good. and you always start taking food in that path, in that hotel. So you never explore the other hotels in your vicinity. So then what you will never know the other dishes that could be there in the other hotels. So that's the idea. So if you go to a particular place and you get what you want, and if you always take that path, then that is deterministic, which is given here. So which is like on the left. But every day, for example, you don't want to take a new place, go to new place. Some hotels you like, some hotels you badly disliked it. In that case, you don't want to go to new hotel every day. So what you do is, once in a month you try out a new hotel, but most other times you go to the same hotel which you liked earlier. So that's what is the randomness. So where you will randomly pick some other place that you want to have a change, right? Human mind is trained to do that. So for example, human mind always wants a change. So if you always go to the same place, you actually get bored of it. So the boringness is nothing but the Markov decision process. So eventually your brain wants to do something new, and it wants to go to a different place. So that is actually built within our evolution. But if you want to mathematically represent it, that evolution is brought into the mathematical representation using the Markov decision process here. So that is what is the idea. So for example, if the agent is here, if it is it is going to go up, there is a good chance that it will reach the final destination. But if it goes into the right, there is a good chance that you will fall into the fire pit. But if you go in below or to the left, then what happens? So there are some unknown consequences. So will you take it? That's the answer. And for that, what we do is, we actually start introducing some more information here. So to the overall Markov decision, in the overall, what do I say? The action space, what you do is you introduce some randomness. And that randomness in the Markov decision process is actually given here. So what you will want to do is not just the previous path, but you also want to introduce some more randomness into the path. And if I'm here, then what happens is, by introducing the Markov decision process, what you'll do is you will actually start getting new rewards. So what you do is, sometimes when you are here, then what happened was you actually went above and you are able to reach your destination. But some other times, randomly, you also fell into the fire pit. So when I fell into the fire pit, I get a negative reward. Whereas when I move into this direction, I get a positive reward. So what I do is, I will start introducing some difference here. So that way, what happens is, randomly, I try to take all my actions. And then what happens is, um, you create something called as um, a random action. And by being here, I will try to sometimes go in this direction, sometimes in this direction, sometimes in this direction, and sometimes in this direction. So that way I will start learning new things. And when I do that, what happens is, sometimes I fall here, so I get a huge negative reward. So this position gets a really very low negative number. Whereas if I move in this direction, I get a positive number. Whereas if I move in this direction, I will not try to move it because I'll get even lower score. But if you are here, there is an interesting fact. So from here to here, if I see, I get a positive reward of 0.63. Whereas from here to here, if I move, you can see that I get a lower reward, because in this path, I have gone earlier and I have fell into the fire pit. Because of that reason, what I'll try to do is, I'll identify that this route is more riskier, and hence I'll try to avoid. And you can see that.
Sir, one doubt. Sorry for the interruption. So
Yeah.
I'm starting from the starting point. Suppose I'm taking in the P2. So once I started, how should I know I'm taking the wrong? Because I don't know the reward here you have mentioned some values like 0.46. The other side, if it is a positive reward, 0.63. So how could I know I'm taking the wrong path? I'll get some reward, 0.46. But this is the lowest reward. So something is there in the highest reward. How should I know that, sir?
Okay. That is again learned by taking the action. So let me give that information here. So for example, we'll have to again go back to the same process. So we get a positive one by reaching here, and we get a negative one here. And right now it is a clean state. For example, you're starting a fresh new simulation. For none of the states, you don't have any rewards at all. Okay. So
Yes.
in this case, if you are here, what can you do? So you can either move. There are two actions. Either you can
Yes.
move forward, or you can move towards the right.
Yes.
So what you do is, the first time the agent moves towards the right.
Hmm.
Okay. So then what
Yes.
happens is, I cannot give a reward, but I add that action.
Okay.
to my queue. And again, I move here and I taken, I note it down, and I move here, I note it down, and I move here, I note it down, and I move here, I note it down, and finally I get a +1.
Mm.
So at this stage, from this state, taking this action gave me the reward of +1. So what I'll do is I'll put that reward here as +1. So that's how this reward is achieved here.
Okay, sir.
So now what I do is in my queue, I have a set of actions. So for example, uh, let me put those states. So for example, this is S1, this is S2, and this is S3 and so on. So you have a series of states, and for each of these states, you have taken some action. For example, moving right, moving up, moving left, and so on. You have taken some actions. So now you have this details here. So for example, from S1, so for example, let's keep it this way. So move right. So I'll put that right is actually A1, which is action 1,
Mm.
and left is actually uh, A2. So I can actually define what is that exact action. So
Okay, sir.
this is called as action space. So again, moving top is actually action 3, and moving below, which is, let's say, low. So I give action 4. So now what happens is at S1, what is action I've taken? I have taken A2. Next is at S2, again I have taken the action A2. Whereas uh, in the case of S3, I'm taking action which is A1 because I'm moving top.
Yes, yes, right.
A3, right? And then at S4, again I'm continuing with moving towards the top. And then finally at S5, I have taken the same action which is A2. Sorry, I think throughout I should have, let me change these two. So moving right is actually what is I have given, try to give as A2. Maybe this one will be. So you can see that everywhere, whenever I've taken to the move toward the right, I've taken as A2. So this is the set of actions. So finally, at S5, taking action A2 gave me a reward of +1. So this is where I finally get a reward.
Yes.
So what I will do is I will actually go and set the reward of +1 that I received here. I will start applying the discount factor as per the Bellman equation that we have seen earlier. So we will apply the rewards. So that's how it comes. So you can see that if I don't put a discount, what happens is the path that I have taken, I will put a +1 for each and every one. So from here, so I will get the +1 here. So from S2, S3, by moving towards the top, I got +1. So I will put +1 here as well. So if you do that, when what happens is every path will get the same +1. So next time, if I move in this direction, what happens is I will put a +1 here, +1
Yes.
here, and +1 here. So this is what is the problem, which we discussed earlier. So when the
Yes.
agent is here, it will get confused if it gets +1 in both directions. So you can see that it can either move here or move here, and it will get the same reward of +1. We don't want that. So which means if the agent is here, we want it to move in this direction. We don't want it to move in this direction.
Mm.
That is the reason we have put a discount factor in such a way that what happens is, if you put a discount, what happens is, for example, here the reward is 0.81, so here the reward is 0.73, and here the reward is 0.62 or 62, whatever it is. So now if you see, if the agent is here, if it moves downwards, its reward is 0.62. Whereas if it moves towards the right, it gets a better reward. So that way what happens is it will learn to move towards the right, and it will not try to move below. So this is how the reward distribution happens. I hope it's
Yes.
clear.
Yeah. Yes.
Okay. So I will
Yes.
also give the randomness information. I hope that is the next step. So this is actually the discount factor, which is introduced by the Bellman equation, and this is the Bellman equation. So the Bellman equation says that the reward for the current state should always be the reward for the next stage that was taken uh, plus the reward at the current stage. So that's what is the Bellman equation, and you apply that, you will get this discount factor based path. So this is actually the list of rewards that you get for each path, and through this you can create something called as a policy. So that is our plan. So based on these values, you can actually create a plan in such a way. If you always move in the path that will give me the maximum rewards, you will take the right path. But again, there is a two paths that are evolving when you use this particular Bellman equation, which just only has the discount factor. So what you do is, if you start introducing randomness and make the agent take many actions over a period of time, sometimes by taking the path that actually has a higher risk, what happens is it will start receiving a lot of negative rewards. And eventually, by using that negative reward, what I will do is, if I use the same equation with the negative reward, with the randomness, you'll observe that gradually, after several simulation, the agent, when it goes through the path P2, it'll start falling into the fire pit more frequently. Hence, its rewards in moving in that direction will become lesser. Whereas the path that is less riskier, if it starts moving in that direction, it'll more likely reach the target. So which means the path that is more safer and less riskier will start getting higher rewards, and paths that are more riskier, there are more chances many times that you could have gone into the wrong path, and hence it will start avoiding that path. So that is what is the idea behind introducing the Markov decision process. So that way, what happens is, now if you see, if you convert this into a plan, what happens is you are always going to take the P1 path that we discussed earlier. And if for any reason, unintentionally, if you moved from here to there, you can actually see that the consequence. So for example, you move towards the wrong path. So for example, randomly you moved from here to here. Then what happens is you should immediately turn back and move in this direction. So that's what is supposed to be the right path. So how do you enforce it? By giving this kind of a where is it? This kind of a path rewards. So now if you see, I'm getting 0.455 here at the starting position. I get a 0.46 here and 0.36 here, because the more closer I'm to the fire pit, the higher risk I'm at. So that way, what happens is the agent will stop, not try to go into that particular direction. Whereas unintentionally, as I showed, if it moves in this direction, if I'm already here, then what is the path? I should not try to move here. Instead, I should move here, so that I can still try to eliminate this moving in this direction. So that is what we are ensuring by introducing the Markov decision process here. Are we clear? Any questions so far?
Yes, sir, it's clear.
Okay. So
Sir, you have chosen here Markov stochastic processor like that.
Yes.
Is there any other algorithm for machine learning? We have a lot of algorithms like that. If I'm going for this, is there any different kind of algorithms I have to
Okay. So I wanted to introduce this at the initial time, but I didn't have time to discuss. For example, how will you normally take an ML model? So for example, you create your data. So for example, you import your file .csv. So you get your input data. Then what you do is you create an object of your ML model. So for example, linear classifier, or let's say SVM classifier. So how do you create it? So for example, SVM, and you create an SVM classifier. So SVM classifier dot train, and what do? You pass your input data, and the output of the training process, you will get your ML model, right? So this is how it works, and I'll call it as SVM model. Okay, so this is how you build your model. So what do you typically do? So you actually build multiple models. So instead of SVM, let's say SVM classifier, right? So instead of SVM, for example, I go for random forest. So you take your random forest, I'll call it as RF model, and I take the RF model dot train, and I'll get the I get the RF algorithm. Okay, so I take the RF algorithm object and I train with the same data. I'll get a random forest model. So this is how you get different models. So your data is there and you train it with a different algorithm. The train function you are not writing. So in fact, the train function will internally use something called as a loss function. I didn't go into that level of details, but actually the loss function will be there. That will calculate for a given data. If there are certain predictions, the difference between the prediction and the actual will be calculated as a loss. So whichever the more efficient the loss function is, the better your learning will be and better model you will get. So the loss function, usually you will use something inside the loss function. You will have something called as a gradient descent, which will be the internal algorithm that will be the learning algorithm. So the loss function will internally use a learning algorithm to create the next set of weights. So these are some of the internal details that I didn't have time to cover today. But uh, if you see, you don't implement the gradient descent, you don't implement the loss function, you just use the pre-built model, you use the pre-built loss function, you use the pre-built learning algorithm to actually train your model. So machine learning is much more simpler. But in the case of reinforcement learning, AI algorithm, so you have to write both the loss function as well as the learning algorithm. So which means learning algorithm, writing a different learning algorithm is far, far more tougher. Okay. So both the loss function and the learning algorithm you will be writing, and that is where the AI is. So when you build an AI model, you are writing your own loss function and you are writing your own learning algorithm. So writing these two is not so easy. And the problem is, if you want to build a better AI, you have to write a better learning algorithm that is better than the best that is written by someone else. So that is the reason it is far more tougher. I hope you understand the difference. So when you
Yes,
build the
yes, I
AI,
got it,
so
sir.
you write
Yeah.
your own loss function and you write your own learning algorithm. So it is not very simple as like calling the train.
Yes, sir. Not so simple.
So when you use AI, mostly creating this agent, creating this learning environment, and all that is not going to be easy. Okay, so I think we discussed about it some time back. Yeah. So creating this environment, simulating the physics, and all that is very, very tough. So our objective should not be to create the environment or creating the agent. So because of that, what they've done is there is an initiative that was created, which is an open source project, which is called as Open AI Gym. So the OpenAI Gym initiative, what they do is they have pre-built environments and the action space and rewards. All of those are actually pre-built. So what you can do is you can only focus on writing your loss function and algorithm, and you can forget about creating the environment and creating the actions and rewards. Okay, so there are a lot of pre-built environments available which you can use. Pretty much all people who work on AI use this software almost always to actually uh, work on AI algorithms. So let's look at the OpenAI Gym uh, website. So OpenAI Gym, OpenAI.com, that's their website. So if you get into their uh, website, yeah, so you can see there are a lot of games that they have used. So the reason that we use games is because we don't want to actually put a real complex robot and train our algorithm. So simple concepts of algorithms can be trained with very simple learning processes. So we mostly use these games to actually prove the efficiency of an algorithm. If, for example, my learning algorithm able to win 90% of the games after 50 iterations compared to another learning algorithm winning just 50% of the games after 1000 iterations. So in that case, my learning algorithm is faster in capability in learning compared to someone else's algorithm. So to prove that, what we do is we usually use these kinds of game environments to train our model. And you can see that. So how fast is the learning? How fast is the loss dropping? How fast is the algorithm learning? In how many iterations it is learning? And so on. So those kinds of information we actually give measure, and that's how the uh, environments. If you check, you will actually be able to see a list of environments that are available here. Okay, so you can actually load them in your code and very easily develop your algorithms on those kind of environments. So if I check the spaces, so for example, there are different uh, levels of things that are there. I have set up, it's really tough to actually set this up. When we did it around 5 years back, most of the environments are having some kind of a instability, and when we load it, it will suddenly crash. So when it crashes, you don't know whether the crash is because there is a bug in your code or there is a bug in the environment. You don't know, and it takes a lot of effort to actually troubleshoot and fix those issues. We have faced all of that, and we have developed a few algorithms for internally for our research purposes. So this is typically how we build it. And in fact, I have set up an environment in my machine, but I'm not sure if I have the link to it. So for example, if I go to my Anaconda environment, so let me just open Anaconda. So let me just check my Anaconda env list. I've built some environments which I've set up in my Windows laptop, and I think I've used a PyTorch environment to actually train my model. I'm not sure if I have that environment in this laptop. I think I don't have it. I've built some AI environments, but that's in a different laptop. So it takes a lot of effort to actually build the environment. Let me see if I can show you some steps to actually create such an environment. Excuse me. Mm. Okay, so I don't have the environment files. Probably to Sumati madam, I'll try to share some steps on replicating the AI environment which you can use to train such a model. I'll also share some source code files which you can use to actually run AI algorithms. There are some pre-written sample code that's available in the OpenAI gym that you can actually use to train your models. I'm not actually able to get it because the OpenAI gym website, they've changed a lot of things. So in the homepage itself, they list a lot of environments earlier, but right now they've actually removed most of that information from here. So let's see if there is anything on the get started. Okay, I think they changed it a lot. So I have used to set up either TensorFlow, Keras based environment or PyTorch based environment to set up the AI, and we used to load the environment and actually run some code with it. But I'm actually not able to see that code here because they changed a lot of their application. Yeah, this is what I wanted, but. mm, Yeah, so these are all different environments that we use. So for example, two-legged bipod trying to walk, and for example, two-legged dog kind of, you remove the four-legged animal, you remove two legs, and can it still walk? You can even simulate that. So that is this particular exercise. And for example, making a spider eight-legged animal walk, four-legged animal walk, and balancing a pole. So these are all some of the simple games that are used in the OpenAI gym. But apart from that, there are much more complex things like role-playing games, like for example, even things like GTA. So this is actually called as Doom. Even we are actually, I have set Wisdom for some of my environment setup in my previous projects. I'm not sure if I'll be able. Yeah. So if you get into the archive papers, you'll actually be able to see how they compare their learning algorithms. I think we can actually archive is the best place where you can actually learn, get the maximum learning from here from the net. So if you check the archive, they even give you the full paper. You don't have to pay anything. So all papers are free. You can download the PDF form of your papers. And finally, they publish their report their learning algorithms efficiency through this. Let me see if I can download and actually show that in more easier to view form. So let me try to open it. Yeah. So if you see, what is the efficiency of their learning algorithm compared to other algorithms? So most people compare their algorithms uh, with this setup. So for example,
So they used to in this kind of research, people will be used to compare the algorithm in terms of what, sir? What are the main
let me show that to you. So for example, there was a company that was acquired by Google around 7 years back. So it was called as AlphaGo. So AlphaGo algorithm, they created an AI algorithm that actually played a game called as Go, and it defeated the world champion at that point of time. Okay, so if I show you the AlphaGo paper from the archive, you'll actually be able to see the simulation and how they compare their results with the different algorithms. I'll try to see if I can show you that information. I'm sorry, I'm extending the session. Yeah, you can see that here. So these are three algorithms, and for each algorithm, what is the number of wins and draws? So
Okay.
in how many simulations they compare it, and they take a particular game and they compare it. Sometimes what they do is they take multiple algorithms. So in this case, they've only taken chess, but what they do is they actually um, uh, uh, identify the robustness of the solution. For example, if you create an algorithm that can only be suitable for a particular only a particular situation,
Yes.
then it is not robust. But if you create a general learning algorithm that can go and apply to any environment, then it's a much more robust environment. So what they do is using the same algorithm, they actually train on all possible kind of environments, and they validate their outcomes with, for example, the outcome of other algorithms. And then what they do is for each algorithm, what is the efficiency, how many wins was it able to do, or how soon was it able to learn. So those kinds of, how soon is the loss dropping. So that kind of comparison they do. I used to have a lot of papers, but I actually changed my laptop, so actually I'm not actually able to show that information. um, Let me see. AlphaGo. Yeah, so this might be more a generic. So what they do is they don't just make the algorithm play only one particular environment. They make it play on a variety of environments, 10, 20, 30 environments. And for each environment, how fast is the algorithm learning? So those kinds of metrics will be collected. And they finally, they publish for each and every environment on which the algorithm was tested, what was the uh, performance characteristics of that algorithm. They tested, and not just their own algorithm, they tested for so many different other algorithms as well. I'm actually not able to get the paper. I'll see if I can maybe post the session. I'll try to share the details to Madam. Paper. I'm actually not able to get that immediately right now because I've already exceeded the time. Uh,
Yes, sir. No problem.
in Git, most people even publish the code that they have used to actually uh, train the models, and you can use it. But setting up the environment can be a challenge. But mostly, if they have set it up, they will also give you environment file which will have all the dependencies with the right set of versions for each and every software. So if you work with Python, mostly you will be able to use that file and replicate that environment, and on that environment you can run the project. But sometimes what happens is it might still fail to run if you don't have a GPU, because most of those algorithms take a very, very long time and they require a lot of compute resource to run. So mostly they would have trained it on GPU based environment like a PyTorch GPU or TensorFlow GPU. So without the GPU, probably that algorithm might still fail. It depends. Some algorithms will run if they've given the environment for without GPU, while others might fail without the GPU. So it depends. So you have to make a lot of trial and error to actually get the best code that works. But definitely will get code. That is for sure.
Yes, thank you, sir. Thank you.
Yeah, let me see if this paper loads and if I can show some details, it'll be fine. Otherwise, I can still. So mostly the results will be discussed at the end with all the games that it took. Okay, so this also does not have all the games. So they've only compared two algorithms, but usually what happens is they compare the uh, algorithm with so many other algorithms. So, for example, at that time, there could be 10 or 20 different algorithms. And against all of those algorithms, the most leading algorithms in the world, they will validate their results and they will prove that their algorithm always performed better than all the other algorithms. And they even tabular chart the results. So we can see the so mostly what happens is if the learning algorithm is not good, so up to certain number of iterations, the learning will be good, the gain will be there. But at one stage, the learning will stop, and the algorithm learning stops. When it stops, it actually goes to a flat curve. So you will actually be able to observe that here. So you can see that the red line here is actually an algorithm that was not able to learn at one stage and it stopped learning. Whereas there are other algorithms that are not so stable. You can see they will at certain stages the algorithm learns and other times it fails. But one algorithm can continuously keep learning, and even over a long period of iterations, it can still learn. So those are the algorithms that we typically take for.
Sometimes we may not consider the iterations, that learning process is must.
Yeah.
So maybe, yeah, it might be a lot of iterations, still that learning process. Got it, sir. Got it, sir.
Fine. If there are any other questions, please let me know, madam. I think I'm done from my.
Participants, is there any questions? Okay. No questions, then we can conclude the session. So really, it's so how to say thanks? Simply, we cannot say slightly a single word thanks. Yeah, very good explanation, and we got a better idea of reinforcement learning. So far, we know so many things: machine learning, deep in Q, like so many things we are learning. But still, even so, the past 1 week before, I was thinking about the reinforcement learning and other things. So really, I got so in my experience, I got an excellent. An explanation about the reinforcement learning, sir. Really, it's a good presentation. We cannot say it's a presentation, good teaching. So you taught very well. So I think, hope all our participants got a good experience of learning this particular thing. Thank you so much, sir.
Thank you, madam. I'm just showing you the code of one of my reinforcement learning algorithm. Can you take a minute just to explain what it is?
Yeah, please.
Okay. So this code, if you see, we take a model, which is this network. And what we do is you can see the replay memory. So this replay memory is nothing but, so for example, the same thing that we discussed in one of our earlier steps. Here, if you see, so what we do, we put all our experiences in a queue. And then we replay one after the other each of these actions and each of these states. So that's nothing but this replay memory here. So when you replay the memory, what you do is you take an event. An event is nothing but it will have the current state and the current action from the memory. And what you do is when you take that, you actually take a, for example, this is a deep Q learning algorithm. So what it'll do is for each and every action you have to take. So for example, in your current state, what is the next action you have to take? So for that, whatever model you have built, what you'll do is you apply the current state, and then you will get an action. And the action is considered as a probability. And if you remember, I told you that we will be doing markup process. So what we do is 80% of the time we will use the model's action that is predicted. Whereas another 20% we will actually use some random action. So if you see the select action, you will be able to see the action here, but we will not always use the action. So there is a condition. So what we do is for 80% of the time, we will use the action that is given by the model. But another 20% of the time, we will actually introduce some randomness. I think this one does not have that markup decision process, but we will actually put that here. So instead of that, so for example, we will say we'll put an if condition here. So 80% of the time, randomness, we will actually use this current action. So rest of the 20% time, what we do is we text, for example, self dot action. We will actually use, for example, action state of random. So what we'll do is we will actually take some random action. So that way, what happens is in the remaining 20% of the time, you actually take a random action. So this single line will actually introduce the markup decision process, which is not here. Okay, so that's a small place where you will introduce the markup decision process, and you can see for each state what is the current action, what is the next state it reaches, and what is the reward at that position. So you get that. Okay? So this is how you actually train. And for each and every action, so what you do is you actually have a reward window, and this score calculation is nothing but the discount factor multiplied by discount factor, and you get the score. So that is this. And to load the model, if you see, this is the way to load. So what you do is I think I might have used Wisdom, or I have used Kiwi here. So in the Kiwi, there are a lot of environments that are available. And what I would have done is I would have loaded one particular environment here. So let me see if I can show you the load environment option that is done. Okay. One minute, sorry. Okay, so let's see the game. So what we do is object property, and we create a game. And this car object here is nothing but the agent. And these three are actually nothing but some additional objects that we have created. As for example, if the car is going to hit a particular obstacle, so it will hit one of the positions in front of the car. So these three balls are actually related to that. And in this, if you see, we even calculate the velocity of the car, how fast will it, or how farther will it move in its environment. All that information is given here. So this car object here is actually nothing but, including the agent, it is actually the environment plus agent put together. We created or loaded it as actually an object here, as car here. So let me see. Yeah, car app build. You can see the game. So if you see the game, to the game, I can actually specify what is the object that I want to create. And in the environment, if you see, we would have actually loaded a particular environment. So for example, if I want to load uh, a Doom environment, then in that case, that environment will be available just as an import statement. You just import it and you run the load command, it will load it, and then your agent will be at the initial position. And you can start taking action, and it will take the agent to the next position. So that's how it is done. And everything is actually done using code here. And you can see there are certain buttons that you can actually control. For example, the user can actually save the model at a particular state. Even for that, there will be some options there. Okay. So I'll try to add this code or share this code to you post the session. Fine, madam. I think I'm done for today. Thank you. And,
Yeah, thank you, sir. Thank you so much, sir. Still, any questions from the participants? Okay. Now I request Mr. Karthik, Assistant Professor from Information Technology Department, to give.
So thank you, sir. It was really an informative session. So on behalf of the Department of Information Technology and Computer Science, Sri Ramakrishna College of Arts and Science, I extend a really heartful vote of thanks to our guest, Mr. Sai Natarajan, who spared his time from his busiest schedule to grace the occasion. So today we all had an opportunity to hear your thoughts on reinforcement learning, and this will surely help us in our future events. So once again, I thank you, sir. So I also thank all the participants who have joined for today's session. Thank you all.
thank you, sir. Thank you all. Shall we conclude? Shall we drop from the meeting?
Yes, sir.
Thank you, everyone. Okay, there was a request to share my contact. I have put that in the chat.
Yes, sir. Yes.
Thank you. I think I'll drop from the call. Thank you, everyone. Hopefully, it was helpful for you to proceed with your AI journey. Thank you. I'm dropping from the call. Thank you.
The feedback link is shared in the post chat box.
And tomorrow, as usual,
So tomorrow, as usual, we have the session at 2 p.m.
After this FDP, that quiz will be posted in your WhatsApp group. You have to attend the quiz. So based on that, you will receive your certificates.